All right, welcome to this explainer. This one is designed exclusively for you, grade 9 geometry students at St. Paul American School Clark. Today, for Unit 2, Lesson 2, we're going to completely demystify parallel and perpendicular lines. We're moving way past just trusting our eyes here. Instead, we're jumping straight into the foundational mathematical truths that dictate exactly how lines interact on a coordinate plane. Just to help you focus your learning, here is our roadmap for today's analysis. We'll start with a lesson objective, define those line relationships, walk through a worked example, check out some common misconceptions, do a quick formative check, and then wrap it all up with a concise recap. Let's get right into it. First up, lesson objective, your geometry goals. So, by the end of this explainer, you're going to be able to flawlessly identify these line relationships and, most importantly, use slope to write their exact equations on a coordinate plane. We are moving far beyond just basic visual recognition here. You'll learn exactly how to use algebraic slope to write precise line equations, basically mathematically proving that lines are parallel or perpendicular, rather than just guessing based on a quick glance. Okay, moving on to defining line relationships, the formal boundaries. It turns out relying on a gut feeling for how lines look often leads to errors. We've really got to rely on strict formal definitions. Parallel lines maintain an equal distance, they literally never intersect, and they travel in the exact same direction within a plane. Perpendicular lines, on the flip side, absolutely must intersect, and they have to form a perfect 90-degree right-angle framework. When we compare them directly, it's pretty clear that parallelism is all about absolute separation, right? While perpendicularity requires a very specific, perfect intersection. If we look at the algebra behind this, parallel lines have an identical slope. But for perpendicular lines to hit that exact 90-degree mark, they have to have opposite reciprocal slopes. So, for example, if one line has a slope of 2, the perpendicular line must have a slope of -1/2. All right, let's look at a worked example, the algebraic model. Here is the exact 4-step procedure you can use to write the equation for a new line that passes through a specific coordinate. It's almost like a geometric recipe. First, identify the given equation, like y equals 3x plus 5. Second, extract the original slope, which is 3. Third, you keep the slope identical for a parallel line, or you flip the fraction and reverse the sign for a perpendicular line. Finally, step 4, substitute your new coordinate point, like 0, 2, into your new equation to find the new y-intercept. And this brilliantly illustrates how our algebra directly controls the geometry. An equation isn't just a bunch of numbers. It's a set of strict instructions dictating exactly how this line interacts with point A on this specific grid. By applying those 4 steps we just talked about, you've got the power to draw a line perfectly through target point A that will either run exactly alongside that first line forever without touching, or cross it at a flawless 90-degree intersection. Now for the misconception check, where real students get stuck. So it's actually a super common mistake to think that parallel lines are simply lines drawn opposite to each other. Instead, we really have to look at the accurate mathematical models which correctly prioritize the rigorous 90-degree intersection for perpendicularity. If you don't anchor your understanding to that formal 90-degree angle rule or the non-intersecting identical slope rule, it is incredibly easy to misidentify lines on a graph. And hey, it is perfectly normal to make mistakes here. Take this quote from a real student who falsely believed perpendicular lines must always be perfectly horizontal and vertical. But as we know, a 90-degree intersection can happen at literally any slanted angle on the grid. This is what we call a prototype misconception, believing that just because you first saw perpendicular lines as a perfectly upright cross, they must always look exactly that way. Geometry is dynamic, guys. As long as their algebraic slopes are opposite reciprocals, they are perfectly perpendicular. Okay, time for a brief formative check. Test your knowledge. Take a mental second to evaluate this problem. Ask yourself, if you rearrange that first equation into slope-intercept form, do the slopes perfectly match? Well, let's see. If we take 2x plus y equals 8 and subtract 2x from both sides to isolate y, we get y equals -2x plus 8. So the slope of our first line is -2. But the slope of our second line, it's +2. Because those slopes do not perfectly match, we know with absolute certainty that there is no way these lines are parallel. Let's wrap this up with a concise recap. Core takeaways. So the absolutely crucial point here is that your visual interpretation of lines must always be backed up by the strict algebraic rules of slope to guarantee they are mathematically parallel or perpendicular. Remember, parallel lines never intersect and have identical slopes. Perpendicular lines form a 90-degree angle with negative reciprocal slopes. Always avoid that prototype error we talked about. Perpendicular lines definitely do not have to be perfectly straight up and down. And most importantly, visuals must always, always be verified by algebraic equations. I'll leave you with this thought. If algebraic equations perfectly dictate line behaviors on a graph, how might this exact geometric precision be essential for designing the digital screens and physical structures we rely on every single day? Mastering these exact algebraic slopes isn't just about passing a math test, it's about understanding the hidden mathematical framework that safely structures the entire physical world around us. From the digital screens you're looking at right now to the roads we drive on, these geometric rules are quietly at work everywhere. Thanks for joining this explainer, and keep looking for the math in the world around you.